For decades, scientists have looked into the sky and seen a universe overflowing with stars, planets, and potential homes for life. On paper, the galaxy should be crowded, yet our instruments hear only silence. This tension between a universe that looks friendly to life and the absence of any clear signal is known as the Fermi Paradox. Tonight we explore the leading ideas that try to explain where all the aliens might be, or why they might be hidden. If you enjoy calm journeys into big cosmic questions, please like, subscribe and share, and tell us in the comments which solution to the Fermi Paradox do you find most convincing and why. Thank you for watching. Now let's begin. The story of the Fermi Paradox begins on the widest possible stage with the observable universe spread out across space and time. Astronomers look out with modern telescopes and see that the universe is not an empty void but a vast population of galaxies. Each galaxy holds hundreds of billions of stars, and the number of galaxies within the observable horizon reaches into the trillions. In simple terms, there are so many stars that language begins to fail, and any attempt to list them one by one would never end. This immense backdrop is the canvas on which the question about alien life is drawn, because the first impression is that the universe looks generous, not stingy, when it comes to places where life could exist. Light from distant galaxies travels for billions of years before it reaches Earth. Those galaxies are seen not as they are now, but as they were when the light began its journey. That means the observable universe is also a time machine showing scenes from many eras at once. Some galaxies appear as they were when stars were first forming. Others are seen at more mature stages filled with heavy elements forged in earlier generations of stars. Many of these elements, such as carbon, oxygen, and nitrogen, are the same building blocks used by life on Earth. Nothing in those distant scenes looks unique to one special place. Instead, the same basic ingredients appear again and again. The physics that shapes those galaxies is simple in outline. Matter clumps under gravity. Gas clouds cool and collapse. Stars ignite in their centers, shine for long periods, and then die in ways that spread heavy elements back into space. Over time, the raw material for new generations of stars becomes richer in those elements. In galaxy after galaxy, this cycle repeats. Once the first stars have lived and died, the conditions for rocky planets and complex chemistry start to appear naturally. From a distance, there is no obvious reason why this process should favour only one corner of the cosmos. Large surveys carried out by space observatories and ground-based telescopes show that galaxies come in many shapes and sizes. Spiral galaxies like the Milky Way mix orderly rotating disks with regions of star formation. Elliptical galaxies hold old stars in smooth swarms. Irregular galaxies show more chaotic structures. Yet across these different forms the same pattern holds. Stars are common. Planets, as later surveys reveal, are also common. Cold gas, warm dust, and the radiation from countless suns mix together in environments that look, at least in principle, capable of supporting rich chemistry. On the larger scales, the distribution of galaxies follows a web-like pattern defined by invisible dark matter and the pull of gravity. Filaments of galaxies stretch across hundreds of millions of light-years, separated by great cosmic voids. Within the bright strands of this web, galaxies cluster together, sometimes colliding and merging, sometimes passing close enough to disturb one another. These interactions drive waves of star formation and stir up gas that might otherwise remain quiet. Over billions of years, this restless activity spreads heavy elements far from their birthplaces, seeding wide regions of space, with the materials that planets and potentially living organisms can use. The age of the universe also matters for the Fermi Paradox. Observations of distant galaxies and the expansion of space suggest that the universe has been evolving for more than 13 billion years. That is long enough for many generations of stars to have formed and died, and long enough for rocky planets to have cooled, stabilized, and perhaps hosted chemistry that leads to life. When scientists consider the sheer number of stars, the long timescales available, and the repeated cycles of enrichment, they see no obvious shortage of opportunities. Even if the probability of life starting on any given planet is low, the number of trials offered by the universe is enormous. In everyday terms, the cosmic deck seems stacked in favor of life somewhere. Modern cosmology supports this view in another way. Measurements of the cosmic microwave background, large-scale galaxy surveys, and the chemical content of the oldest stars all point toward a universe that is uniform in its basic rules. The laws of physics appear to be the same in distant galaxies as they are in the Milky Way. The relative amounts of hydrogen and helium, the light elements forged in the earliest moments after the beginning of cosmic expansion, are very similar everywhere that can be measured. This uniformity implies that whatever allowed life to arise on Earth is not the result of a bizarre local exception. The same kinds of atoms and the same basic forces work through the entire observable cosmos. Within this setting, the Fermi Paradox takes its first quiet step into view. If the universe is so fertile in potential habitats, if the ingredients for chemistry and biology are spread so widely, and if time has been so generous, it seems natural to suppose that life might have formed not only once, but many times on worlds scattered through countless galaxies. At this point in the story, the idea of alien life is not yet a contradiction. It is a simple extension of the same reasoning used to understand stars and planets. If ordinary physics can make suns and worlds by the billions, perhaps the same ordinary physics can also make living cells wherever conditions allow. On the scale of the entire observable universe, the Fermi Paradox is still distant and unnamed. The stage is one of abundance and opportunity, and any quiet that is noticed in the sky can be explained away as the limit of current instruments. Space is vast, the signals that might leak from distant civilizations are faint, and the surveys performed so far cover only a tiny fraction of all frequencies, directions, and times. From this wide vantage point, the expectation of life elsewhere begins to feel almost modest. The universe does not look hostile to complexity. It looks patient, old, and rich in experiments. Yet that same sense of generosity will later collide with a stubborn fact. In all this immensity, with all these chances, clear evidence of other minds has not yet been found. The disconnect between what the cosmos seems to allow and what has actually been seen is the heart of the paradox, but for now the focus remains on the fertile backdrop itself, a universe that appears to invite life even as it keeps its answers out of reach. Within this immense cosmic landscape, attention turns to a single galaxy that becomes the main setting for the Fermi Paradox, the Milky Way. From Earth, the Milky Way appears as a pale band across the night sky, but modern astronomy reveals it as a vast rotating disk of stars, gas, and dark matter wrapped around a central bulge. In broad terms, this galaxy holds several 100 billion stars spread across a diameter of around 100,000 light-years. Many of these stars are similar to the Sun in mass and temperature, while many more are smaller and longer-lived. Altogether, they form a crowded environment in which orbital systems, planets, moons, and asteroids are expected to be common rather than rare. Seen in this light, the Milky Way is not an exception among galaxies, but a typical example of a spiral system with many places where life might appear. Over the past century, astronomers develop a clearer view of how stars in the Milky Way form, evolve, and die. Giant clouds of gas collapse under gravity to create new stars, often in clusters where many stars of different sizes are born together. The most massive stars live fast and end their lives in powerful explosions that distribute heavy elements into the surrounding space. Smaller stars, including those like the Sun, live for billions of years and provide long periods of steady energy to any planets that circle them. Each cycle of star birth and death increases the amount of heavy elements in the galaxy, enriching the raw material from which new planets can form. This slow build-up of metals, as astronomers call elements heavier than helium, is important for habitability. Rocky planets' stable surfaces and complex chemistry depend on these elements being available in sufficient amounts. When scientists map the metal content of stars across the Milky Way, they find that many regions have levels that are friendly to the formation of rocky planets. This leads to the idea of a galactic habitable zone, a broad region where conditions are neither too poor in heavy elements nor too dangerous because of frequent radiation events. In this zone, which includes the Sun and its neighbours, long-lived stars with rich planetary systems are expected to be fairly common. As methods improve, indirect evidence for those planetary systems moves from speculation to measurement. The same exoplanet surveys that show planets around distant stars in other parts of the sky also reveal that planets are abundant within the Milky Way itself. While early discoveries focus on large planets close to their host stars, later surveys become sensitive to smaller Earth-sized worlds in wider orbits. By combining these results, scientists conclude that on average most stars in the galaxy host at least one planet, and many host several. This means that the Milky Way likely contains hundreds of billions of planets, a significant fraction of which may be rocky and located in regions around their stars where liquid water could exist on the surface. Against this statistical backdrop, the emergence of life starts to look less like a miracle and more like a plausible outcome in many places. The Sun, as one example of a stable star, sits in a relatively calm part of the Milky Way. It is located in the outer half of the galactic disk between two major spiral arms, in a region where supernova explosions and strong radiation events are less common than in the crowded inner zones. This quieter environment may play an important role in the long-term stability needed for complex life to evolve. If similar stars occupy similar positions in other parts of the galaxy, they might offer many other worlds the same kind of opportunity. The age distribution of stars in the Milky Way adds another layer to the story. Many stars in the galactic disk are older than the Sun by billions of years. Some formed early in the galaxy's history when heavy elements were already present, but before the Sun and its planets came into being. If even a small fraction of those older stars host habitable planets, then the history of potential life in the Milky Way could stretch back far beyond the age of life on Earth. There could have been worlds with oceans, atmospheres, and complex ecosystems long before the first simple organisms appeared in Earth's ancient seas. This matters for the Fermi Paradox because time is a key ingredient. If civilizations can arise on some of these worlds, they do not all have to start at the same time. Many could be much older than humanity, with vast intervals available for technological development, exploration, or even expansion across the galaxy. On these scales, even slow processes can achieve large results. A spacefaring civilization that spreads from star to star at modest sublight speeds could, in principle, explore or settle large parts of the Milky Way within a fraction of the galaxy's total age. The details of such expansion are uncertain, but the basic point remains that the Milky Way has both the spatial room and the temporal depth to host multiple waves of life and intelligence. Taking all these factors together, the Milky Way presents itself as a galaxy where the ingredients for life and the conditions for long-term stability are not extremely rare. There are many stars, many planets, and long spans of time in which biology could take root and evolve. There are quiet regions where radiation levels are low enough for fragile molecules to survive, and there are rich supplies of heavy elements to build complex structures. From this perspective, the expectation that life could arise more than once in the Milky Way seems reasonable. The galaxy does not show any obvious physical rule that forbids it. Instead, it appears to offer more than enough raw material and opportunity. At this stage, the story still follows a straightforward line. a fertile universe contains many galaxies. One typical galaxy, the Milky Way, contains many stars and planets, along with stable regions that should allow life to persist and change. If life can appear under such conditions, then it seems natural to expect that the Milky Way might host not just one biosphere on one planet, but many biospheres spread across countless worlds. Some might remain simple, others might never move beyond microbial stages, but some fraction might eventually produce complex organisms and perhaps thinking minds with tools and technology. In such a galaxy, the idea that humans are the only intelligent species seems at odds with the weight of the numbers. The Fermi Paradox begins to take a clearer shape against this backdrop. If the Milky Way is so friendly to habitability, if it has had so much time, and if the path from chemistry to biology is not impossibly hard, then the absence of obvious signs of other civilizations becomes harder to ignore. The galaxy looks like a place that should be full of stories, yet from Earth, only one story is confirmed. The tension between that high expectation and the lonely evidence is what will drive the paradox forward, as the focus narrows further from the broad star fields of the Milky Way down to the particular history of one planet and the life that studies the sky from its surface. On the scale of the Milky Way, the story of the Fermi Paradox narrows to one particular world where the details of life's arrival can be read in stone. Earth orbits an ordinary star in a quiet part of the galactic disk, but its early history is anything but calm. When the young planet first forms, it is hot and unstable, built from countless collisions of smaller bodies. For a long time, the surface is partly molten, the atmosphere is thick and choking, and impacts from space are common. This violent beginning might seem like a poor setting for the delicate chemistry that living cells require, yet it is also the stage on which those chemicals are assembled. Water arrives in large amounts, probably carried by icy bodies and released from the interior. Carbon and other essential elements collect in the crust, the oceans, and the air. Gradually the surface cools, continents begin to form, and a more stable hydrosphere appears. At the same time, the wider solar system remains cluttered with leftover debris. Asteroids and comets follow intersecting paths, and many of them strike Earth with energies that dwarf any later natural disaster in human memory. Geologists describe an era of heavy bombardment in the early solar system, a long interval during which large impacts are frequent enough to reshape entire regions of the crust and briefly sterilize surface environments. The exact length and intensity of this era are still refined by new data, but the broad picture is clear. For hundreds of millions of years after Earth's formation, conditions on the surface are harsh. Temperatures frequently climb high enough to disrupt complex molecules, and large regions can be melted or vaporized. Under such circumstances, it is difficult for fragile chains of organic compounds to persist for long periods. Yet the record preserved in ancient rocks points toward an outcome that defies simple intuition. When geologists and geochemists search the oldest surviving rocks on Earth for traces of life, they find indirect signs in the form of chemical ratios and structures that are best explained by biological activity. Fossil-like shapes of microbial mats, layered structures in sedimentary rocks, and variations in the relative amounts of certain carbon isotopes all suggest that life is present surprisingly early in Earth's history. The details of this record are complex and sometimes debated, but the general trend is that evidence for life appears almost as soon as the planet becomes stable enough to host it on a long-term basis. In earlier decades, textbooks often describe a comfortable gap of around 1 billion years between the formation of Earth and the first clear signs of life. That interval seems to offer a wide window for gradual experimentation by chemistry. As research progresses, however, the estimated timing of life's earliest traces moves steadily closer to the end of the heavy bombardment. Some lines of evidence suggest that by less than 1 billion years, after conditions become moderately stable, and perhaps in only a few 100 million years, microbial life already covers parts of the ocean floor and shallow seas. In other words, once the surface is cool enough and liquid water is present, life appears to start relatively quickly. This does not mean that the detailed steps from simple molecules to self-replicating systems are understood. Laboratory attempts to reproduce every stage of this transition remain incomplete. Many routes are proposed and no single path has been confirmed, but the geological record indicates that whatever path nature takes, it does not require endless ages on Earth. The time between the end of globally destructive impacts and the appearance of stable biosignatures is small compared to the total age of the planet. To scientists thinking about life elsewhere in the galaxy, this pattern carries an important message. If life took an extremely long time to arise on Earth close to the full age of the planet, then it might be reasonable to assume that the process is usually slow and difficult, and that only a tiny fraction of habitable worlds ever produce living cells. The shorter the gap becomes, the less comfortable that assumption appears. If life takes hold as soon as conditions are broadly suitable, then the underlying chemistry might not be fragile and unlikely. It might instead be a natural outcome when water energy and the right elements are present for some modest span of time. Earth then becomes not an improbable exception, but a typical case of what happens on many wet rocky planets in stable orbits. Additional support for this view comes from the observation that the basic building blocks of organic chemistry are not limited to Earth. Astronomers detect complex carbon-based molecules in interstellar clouds, in the atmospheres of giant planets, and on the surfaces of icy moons and comets. Meteorites that fall to Earth carry amino acids and other organic compounds that formed in space. These findings show that the raw ingredients for life's chemistry can assemble in many environments. A planet like Earth does not have to start from zero. It inherits a rich mix of molecules from the wider cosmos and then subjects them to cycles of heating, cooling, concentration, and reaction in oceans, lakes, and hydrothermal systems. Within this view, the early appearance of life on Earth is part of a much larger pattern in which the universe tends to build complexity whenever conditions allow. For the Fermi Paradox, this is a significant step. If life can arise fairly quickly on at least one suitable world, and if the ingredients and conditions that support this process are widespread in the Milky Way, then simple living systems might be common. Microbial mats, biofilms on rocks and drifting cells in alien oceans may be scattered across countless planets. The paradox does not bite yet because the existence of simple life elsewhere is hard to test from current observations. Microbes do not send radio signals or build beacons around their stars. They transform their atmospheres, but those subtle signs are difficult to separate from non-biological processes at interstellar distances. Still, the logic moves forward. A fertile galaxy holds many planets. On at least one of them, life appears quickly when conditions become suitable. Organic molecules seem easy to make both in space and on planetary surfaces. Put together, these facts favour a picture in which life, at least at the microbial level, may be a common response of matter to long-term stability and energy flow. The mystery that Enrico Fermi later gives his name to does not concern these simple forms. It concerns what happens or fails to happen when evolution has enough time to explore more complex possibilities. If life begins easily, then the total number of living worlds in the Milky Way might be very large. Some of those worlds will have had far more time than Earth to move beyond microbial stages. The question that begins to rise as the focus tightens further is not whether life can start. It is what prevents so many potential living worlds from producing visible technological societies that leave clear marks across the galaxy. Within a few decades, the picture of planets beyond the solar system changes from speculation to measurement. For much of human history, astronomers can only guess whether other stars host worlds of their own. Telescopes show stars as points of light, and any small planets around them remain far too faint and close to be seen directly. The idea of other planetary systems remains an inference based on the way the solar system looks, and on simple arguments about how stars and disks of gas form together. That situation begins to shift in the late 20th century when the first planets around Sun-like stars are detected using precise measurements of stellar motion. A star and its planet orbit a common centre of mass, and this produces a small wobble in the star that can be picked up as a repeating pattern in its light. Soon after another method, the transit method, starts to reveal even more worlds. When a planet passes in front of its star as seen from Earth, the total starlight dips by a tiny amount. By watching for these periodic dips, astronomers can infer the present size and orbital period of planets that would otherwise remain invisible. These techniques are refined and extended by dedicated surveys. Space missions such as Kepler and later observatories stare at large patches of the sky for years, monitoring the brightness of hundreds of thousands of stars at once. From the pattern of dips, they build up a catalogue of planets of many sizes and orbital distances. Ground-based projects continue to improve radial velocity measurements, pushing sensitivity towards smaller and smaller planets. Together, these approaches transform the understanding of planetary systems from a single example, the solar system, to a rich statistical sample spread across the Milky Way. The results are striking. Planets are not rare exceptions, but common companions to stars. Analysis of the Kepler data suggests that on average most stars host at least one planet, and many host several. Small rocky planets, roughly similar in size to Earth, turn out to be widespread, not confined to a narrow class of systems. Planets in orbits where temperatures might allow liquid water on the surface, often called the habitable zone, also appear frequently in the data. Even with all the limitations in current methods, the best estimates indicate that the Milky Way likely contains hundreds of billions of planets, and perhaps tens of billions of worlds that are roughly Earth-sized in temperate orbits. This realization has a direct impact on the Fermi Paradox. It removes one of the early excuses for cosmic loneliness, the idea that planets like Earth might be vanishingly rare. Instead, the galaxy seems to treat planets as a normal part of star formation. Dust and gas disks around young stars routinely fragment and coalesce into a variety of worlds, from gas giants close to their suns to small rocky bodies further out. The diversity is large. Some systems contain planets so close to their stars that their years last only a few Earth days. Others include worlds several times the size of Earth in compact arrangements that do not resemble the solar system at all. But amid this diversity, familiar niches appear, including planets with sizes and estimated temperatures that fall into ranges known to support liquid water and complex chemistry on Earth. With this broader view, Earth no longer sits alone in a small, carefully tuned box of conditions. It becomes one example among many possible temperate rocky planets. The odds that at least some of these other worlds have stable surfaces, long-lived stars and access to water and carbon-rich materials begin to look quite high. In addition, exoplanet surveys reveal planets around many kinds of stars, including small red dwarfs that can burn for hundreds of billions of years. If even a fraction of those systems are quiet enough to be stable, they offer time spans for potential biological evolution that far exceed the age of life on Earth. In parallel with the cataloguing of exoplanets, scientists refine the concept of biosignatures. A biosignature is any measurable feature that indicates the presence of life. On Earth, life alters the atmosphere in characteristic ways. For example, large amounts of free oxygen in the air combined with certain other gases are sustained by biological activity, rather than by simple chemical equilibrium. As telescope technology advances, astronomers begin to plan observations that can separate the light from a planet from the overwhelming glare of its star and spread that light into a spectrum. From that spectrum, they hope to identify gases in alien atmospheres and search for combinations that are difficult to explain without life. Missions under study by agencies such as NASA and ESA, along with future ground-based observatories, are designed with this goal in mind. The hope is that within some decades it will be possible to measure atmospheric compositions for a sample of Earth-sized planets in habitable zones, and to look for signs of active chemistry that resembles the planetary fingerprints of life. The very fact that such plans are being made underscores how far the field has come. A question that once belonged mainly to philosophy and speculation is now framed in terms of target lists, integration times, and instrumental sensitivity. The search for life is no longer restricted to nearby planets and moons. It has expanded to include distant planetary systems that can only be studied through their dim filtered light. At this stage in the story, the expectation of life elsewhere in the galaxy rests on several converging lines. The universe is old, the Milky Way is large and chemically rich. Planets are common, and many of those planets occupy environments that look in broad outline similar to the one that supported the rise of life on Earth. When all these pieces are considered together, the apparent probability that life has emerged on more than one world starts to feel substantial. For the Fermi Paradox, this growing sense of likelihood raises the stakes. If habitable planets are widespread, and life arises quickly when conditions permit, then there may be many planets in the Milky Way that host biospheres. Some of those biospheres might have had long periods of stability older than Earth by billions of years. On at least a subset of those worlds, it seems reasonable to imagine that evolution could have moved beyond simple cells to produce complex organisms, intelligence, and eventually technology. Yet even as the statistical case for life elsewhere strengthens, the observational record remains blank with regard to clear signs of other civilizations. Telescopes detect exoplanets and measure their sizes and orbits, but they do not yet reveal cities, machines, or signals. The discovery of exoplanets thus sharpens the paradox in a quiet way. It shows that the stage on which alien civilizations could appear is far larger and more populated than once thought, while the evidence for any actors on that stage remains absent. As the census of planets in the Milky Way grows, attention gradually turns from simply counting worlds to asking what their surfaces and skies might actually be like, and whether any of them carry the chemical signs of life. In this context, the idea of a biosignature becomes central. A biosignature is any measurable feature that is more easily explained by the presence of living organisms than by non-living processes. On Earth, the clearest biosignatures are found in the atmosphere. The mixture of gases above the surface is not in a simple chemical balance. Large amounts of free oxygen sit alongside gases that would normally react with it and disappear. This imbalance is maintained by constant biological activity in oceans, soils, and forests. Without life, Earth's air would slowly drift toward a different, more stable composition. With life, it is held in a state that is chemically restless, and that restlessness can in principle be detected from far away. For scientists thinking about distant planets, this provides a guide. If a remote observer could spread Earth's light into a spectrum, the pattern of absorption features would reveal the presence of oxygen, ozone water vapor, and other gases in combinations that are hard to explain without a biosphere. The aim of future observations is to perform a similar trick on exoplanets, extracting thin signals of atmospheric composition from the glare of their parent stars. This is a difficult task. A planet is small and faint compared to the star it orbits, and the contrast between them is extreme. To see the spectral fingerprint of a planet's air, astronomers must either catch the moment when the planet passes in front of its star or find ways to block out the starlight so that the planet's reflected glow can be studied directly. Even with advanced telescopes, the resulting data are delicate and noisy, yet steady progress is made. Observations of large exoplanets close to their stars have already revealed broad atmospheric features, including detections of water vapor and clouds. These early successes show that, in principle, atmospheric spectroscopy of distant worlds is possible. Plans for future space missions and giant ground-based observatories extend this work towards smaller, cooler planets more similar to Earth. The goal is to take spectra of a modest sample of temperate rocky worlds and to look for patterns that might signal biology. The set of possible biosignature gases is not limited to oxygen. Methane, nitrous oxide, and other trace gases can be produced by biological processes, and certain combinations of gases that coexist in a long-lasting way are very difficult to sustain without continuous renewal by living organisms. Scientists build models of planetary atmospheres under many conditions with and without life to see which spectral patterns are most distinctive. They also search for non-biological ways to mimic those patterns, because false positives are a real concern. For example, a planet around a very active star might accumulate oxygen through the breakdown of water vapor by strong ultraviolet radiation without the presence of photosynthetic organisms. Dust hazes and surface minerals can also shape spectra in ways that might be mistaken for biosignatures, if not carefully interpreted. In this area, the Fermi Paradox touches a more subtle frontier. The search for biosignatures is not a search for cities or radio transmissions, but for planetary-scale chemistry that hints at microbial life. If such life is common, then there may be many planets whose spectra show disequilibrium patterns caused by biology. Detecting even one clear example would be a profound result demonstrating that life has arisen at least twice in the universe known to science. Detecting many such planets would be even more striking. It would suggest that the appearance of simple life is not rare at all, but a frequent outcome on suitable worlds. In that scenario, the paradox becomes sharper, not softer. A galaxy with numerous living planets, but no obvious signs of advanced civilizations, presents a stronger puzzle than a galaxy where life itself is rare. The gap to explain is not between a lonely Earth and a sterile cosmos, but between many thriving biospheres and a silence in the channels where technology might be expected to speak. Work on biosignatures also highlights the limits of current methods. Even with powerful telescopes, observations will be restricted to relatively nearby stars and to planets that present favorable geometries. Spectra will carry uncertainties, and it may take many years to gather a sample large enough to support strong conclusions. It is possible that future surveys will find atmospheres that look suggestive but not definitive, leaving room for debate about whether biology is truly present. In that sense, the atmosphere of an exoplanet can function as a distant echo of processes that are not yet fully resolved. For the purposes of the Fermi Paradox, however, the exact count of living planets is less important than the trend. If the first detailed studies reveal even a few convincing cases where lifelike chemistry is underway, then the statistical weight shifts further toward a universe where life appears readily given the right conditions. If, on the other hand, spectra from many habitable zone planets show only barren combinations of gases, then the impression of life's ease may have to be revised. Either outcome feeds back into the paradox. A crowded field of living worlds emphasizes the absence of visible civilizations. A sparse field suggests that the first step from chemistry to biology may be the dominant filter. At the time the Fermi Paradox is usually discussed, this observational frontier is still largely in the future, but the direction is clear. Astronomers are building tools that will treat distant planets not as simple points of light but as physical worlds, with surfaces, climates, and potentially living skies. As that transition unfolds, the question of whether life is unique to Earth will move from speculation toward measurement. The answer, whatever form it takes, will either reinforce or reshape the sense of how strange it is that so far the Milky Way gives no unambiguous sign of other minds looking back. From the perspective of the Fermi Paradox, the early appearance of simple life on Earth is only the first step in a much longer and more uneven story. Microbial life seems to establish itself quickly once the surface becomes stable, but the path from those first cells to complex organisms and thinking minds stretches over billions of years. For most of Earth's history, life consists of single-celled organisms living in oceans, lakes and soils, altering the chemistry of the planet in quiet but profound ways. They produce oxygen, fix carbon, recycle nutrients, and build thin films and mats on the sea floor, yet they do not build tools, cities or radio transmitters. If an astronomer were to observe Earth from far away, during these long eras the planet might show atmospheric signs of life, but there would be no direct evidence of technology. This long dominance of simple life forms is an important reminder. It shows that even once life begins, there is no guarantee that it will quickly progress toward intelligence, in the sense meant by the Fermi Paradox, the kind that makes instruments, writes equations, and sends signals into space. Complex multicellular organisms appear only after a very long delay. Fossil evidence suggests that simple multicellular forms exist for some time, but the major expansion of complex animals with hard parts, eyes and limbs, comes relatively late in a burst of evolutionary innovation, often called the Cambrian diversification. Even after this event, many lineages explore different body plans and lifestyles, and only a small subset ever develops large brains. Evolution works without a goal. It selects traits that help organisms survive and reproduce in their local environments. In many habitats, large brains and abstract reasoning do not offer a strong advantage compared to other strategies such as fast reproduction, camouflage, or efficient use of limited resources. The fossil record shows a wide variety of successful life forms, from trilobites to ammonites to dinosaurs, that thrive for tens or hundreds of millions of years without developing what humans would recognize as advanced technology. This suggests that intelligence, as defined by the ability to build complex tools and manipulate an environment on a planetary scale, is not a common endpoint of evolution, even on a world where life is abundant and diverse. Certain features, however, do appear repeatedly in many lineages. The ability to sense the environment at a distance, for example, evolves many times. Eyes or eye-like structures arise in insects, mollusks, vertebrates, and other groups, showing that vision is a useful solution to the problem of finding food and avoiding danger. Limbs and forms of locomotion also evolve in many ways, from fins to legs to wings. These recurring themes indicate that some adaptations are broadly advantageous and therefore appear again and again. Large energy-hungry brains and intricate social behavior are less common. On Earth, only a few groups, such as some mammals and birds, show sustained trends toward high cognitive complexity. Even within those groups, only a tiny fraction of species develop the specific mix of traits that humans display, including fine motor control language, long-term planning, and large-scale cooperation. From the standpoint of the Fermi Paradox, this pattern hints that while basic life may be widespread, the subset of worlds that produce technological civilizations may be much smaller. Another point emerges when survival success is compared between highly intelligent species and simpler ones. Many organisms with modest nervous systems, such as insects, occupy stable ecological roles across vast periods of time. They endure mass extinctions, climate shifts, and continental drift. In contrast, species with sophisticated cognitive abilities, including humans, often reshape their environments in rapid and far-reaching ways, creating new vulnerabilities. Technological power allows such species to adjust their surroundings, but it also introduces novel risks, from habitat destruction to self-inflicted catastrophes. Intelligence of this kind may therefore not be a straightforward advantage for long-term survival. This observation has led some thinkers to suggest that intelligence capable of building advanced technology could be self-limiting. A species that can harness nuclear reactions, manipulate planetary climates, or build powerful machines gains the capacity both to expand and to destabilize its own support systems. On Earth, this tension is visible in the modern era, where human activities alter the atmosphere, the oceans, and the biosphere on global scales. The long-term outcome is uncertain. For the purposes of the Fermi Paradox, the key point is that there may be many planets where life never moves beyond microbial or simple multicellular stages, and a smaller number where intelligence emerges but does not lead to lasting galaxy-spanning civilizations. The timeline reinforces this impression. Earth forms more than 4 billion years ago. Life appears relatively soon after conditions stabilize. Yet complex animals arise much later, and technologically capable humans occupy only a tiny slice of the total history, measured in tens or hundreds of thousands of years at most. If an external observer were to sample Earth's history at random, the chances of finding it in a state with radio telescopes and spacecraft would be small. Most of the time, the planet is either lifeless, populated only by microbes, or inhabited by complex organisms without technology. Extrapolating this pattern to other worlds, it becomes possible that many planets spend almost all their histories in states that would not be obvious to a distant survey looking for artificial signals. Intelligence might flare up briefly in geological terms and then disappear for various reasons, leaving behind only subtle traces in the geological record. From this angle, the apparent absence of detected civilizations in the Milky Way does not yet seem impossible. It may reflect a combination of rarity and timing. Intelligent technological species could be rare, short-lived, or both, and current searches might simply be too shallow or too brief to catch them in the right moment. Even so, the fact that at least one such species exists on at least one world in a galaxy full of potentially habitable planets keeps the central question alive. If Earth is not uniquely favored, if the processes that produce life and complexity are not confined to this one planet, then it seems reasonable to expect that somewhere else in the Milky Way evolution has produced or will produce other minds with tools and curiosity. The Fermi Paradox grows sharper as this expectation is weighed against the continued silence. The story now has several layers. Life may start easily under the right conditions. Planetary systems are abundant. The galaxy is old. Yet the path to lasting communicative civilizations appears narrow, and the evidence for their presence remains elusive. The next step in the narrative is to formalize this tension, to turn vague expectations into more precise estimates, and to see how the numbers behave when all these factors are folded together. As ideas about life and intelligence in the galaxy become more concrete, scientists begin to seek a structured way to talk about how many technological civilizations might exist at any given time. The Fermi Paradox is at its core a tension between expectation and observation, but until the expectation is given a more explicit form, that tension remains vague. In the early 1960s, an astronomer named Frank Drake proposes a simple framework for this purpose. It is later known as the Drake equation, not as a precise formula that delivers a definite answer, but as a way to break down the problem into separate steps. The idea is to start with the rate at which stars form in the Milky Way, then multiply by the fraction of those stars that have planets, then by the fraction of planets that are habitable, and so on, all the way to the fraction of civilizations that develop technology, and the average time they keep communicating. Each term in this chain represents a filter that reduces the initial number of stars to a smaller number of potentially communicative societies. When Drake first writes down this structure, many of the terms are largely unknown. Astronomers do not yet have firm numbers for how common planets are, how many of them are Earth-like, or how often life appears. The equation is used mainly as a discussion guide at meetings, a way to separate different sources of uncertainty. Over time, however, some of the early factors become better constrained. Observations of star formation in the Milky Way provide estimates of how many new stars are born each year. Exoplanet surveys show that planets are common, and that small rocky worlds in temperate orbits are not rare. These improvements shift some of the attention from the first steps in the equation to the later ones, which remain more uncertain. Once the fraction of stars with planets and the fraction of those planets in habitable zones are known to be fairly large, the pressure moves on to the terms that describe life intelligence and technology. To use the Drake framework, scientists and thinkers choose plausible ranges for each parameter based on existing knowledge and reasonable conjectures. One might start with a few stars forming each year, assume that most of them have planets, that a portion of those planets are suitable for life, and that on some fraction of those worlds life actually emerges. From there, another fraction might develop intelligence, and then a smaller fraction still might build technologies that send detectable signals into space. The final factor is the average lifetime of a communicating civilization, measured from the moment it can be detected from interstellar distances to the moment it falls silent. This last term is particularly important because it acts as a lever. If civilizations tend to last for only a short time before they disappear or lose interest in broadcasting, then even if they arise frequently, the number that exist at any given moment can be small. If, on the other hand, technological societies typically endure for millions of years, then even a modest rate of appearance can lead to a galaxy filled with active communicating cultures overlapping in time. When the Drake equation is explored with a range of assumptions, a pattern emerges. Unless several of the filters are extremely restrictive, the Milky Way could reasonably support many civilizations. Even if the emergence of life is rare, intelligence is uncommon, and technological development is far from guaranteed. The sheer number of stars and planets leaves room for a considerable population of advanced societies. Exact numbers vary widely depending on the inputs, but the exercise reinforces a general impression. Under many plausible sets of assumptions, the galaxy does not look like a place where only one technological civilization is likely. Instead, it appears that there could be dozens, hundreds, or even more scattered among the spiral arms, each at different stages of development. As new exoplanet data arrive, some early pessimistic guesses for the planetary terms are replaced by more generous ones. The fraction of stars with planets is high. The number of potentially habitable planets per system may be greater than one in many cases. These updates make the first filters less severe than once feared. In response, some researchers argue that the later filters must be harsher to compensate, especially the ones related to the emergence of intelligence, the development of technology, or the long-term survival of civilizations. The Drake equation thus becomes a kind of mirror. It reflects both the growing empirical knowledge of astronomy and the deeper uncertainties about life and culture. For the Fermi Paradox, the equation does not provide a final answer, but it gives shape to the puzzle. If reasonable values are chosen for each term, the product often suggests that the Milky Way should presently host more than one communicative civilization. Yet when radio telescopes scan the sky, they do not find clear repeating signals that can be confidently attributed to alien technology. The product of optimistic or even moderately conservative estimates stands in contrast to the negative result of systematic searches. Some interpretations of the Drake framework emphasize this tension. If planets are common, if habitable conditions appear often, and if life tends to arise when given a suitable environment, then the early terms in the equation are not likely to drive the final number close to zero. That implies that the later terms must carry much of the burden. Perhaps the fraction of life-bearing planets that produce intelligence is tiny. Perhaps the fraction that develop technology is even smaller. Or perhaps civilizations almost never remain communicative for long on cosmic timescales. Each of these possibilities points in a different direction when it comes to understanding the Fermi Paradox. The equation also highlights another issue. the observable signature of a technological civilization, depends on how it chooses to communicate or operate. The Drake framework originally focuses on radio signals because they are practical to detect with mid-20th century technology. But an advanced society might not use narrow-band radio beams as its primary means of communication. It might rely on methods that are difficult for current instruments to notice, such as highly directional transmissions that seldom cross Earth or entirely different physical channels. In that case, a galaxy could contain many civilizations that do not show up in traditional radio surveys. The Drake equation can be adapted to consider these points, but they introduce additional uncertainties. At this stage in the story, the equation serves mainly as a reminder that the apparent emptiness of the sky is not the only possible outcome of simple reasoning. When realistic numbers are plugged into the structure, the expectation of multiple civilizations seems quite natural, yet the observational record does not match that expectation. The paradox becomes clearer. On paper, a fertile galaxy with many stars, many planets, and long timescales ought to host numerous societies capable of technology. In practice, the search has not revealed them. This gap between estimated abundance and observed silence is what gives the Fermi Paradox its enduring power. It transforms the simple question of where everyone is into a structured problem that can be probed with astronomy, biology, and the study of civilization itself. The next development in this story is to examine how humans have actually tried to listen and look for signs of other minds, and how the results of those efforts deepen the sense that something in this picture is still missing. When the idea of other civilizations in the Milky Way is framed in terms of the Drake equation and the apparent generosity of the galaxy, the next natural step is to ask what has actually been done to search for signs of their presence. The story turns from theory to practice, from estimates on paper to instruments pointed at the sky. In the mid-20th century, radio technology becomes sensitive enough that astronomers begin to consider whether artificial signals from distant stars might be detectable. Radio waves are attractive for several reasons. They travel well through interstellar gas and dust, they can be produced efficiently by transmitters, and they occupy parts of the spectrum where natural background noise can be relatively low. Early pioneers in the search for extraterrestrial intelligence proposed that advanced civilizations might deliberately send narrow-band radio signals concentrated in a small range of frequencies to make their presence obvious against the broad noise of natural sources. With this expectation in mind, the first systematic listening experiments are designed. One of the earliest efforts, often cited as a landmark, involves pointing a large radio telescope at a few nearby sun-like stars and monitoring a narrow span of frequencies for any unusual repeating patterns. These early projects are modest in scope, limited by observing time, computational power, and the small number of frequencies that can be examined carefully. Yet they establish a template. The galaxy can be treated as a field of potential transmitters, and Earth becomes a listening post patiently scanning for artificial radio beacons across the sky. Over the following decades, this approach expands. Larger dishes such as the Great Single Dish Telescope, once operating in a natural hollow, in the Caribbean survey wider regions of the sky with better sensitivity. Arrays of many antennas acting together spread across valleys or deserts are brought into the search. Dedicated programs are set up to piggyback on other astronomical observations, recording radio data while the telescopes pursue their primary scientific targets. Advances in digital electronics and software allow much broader swathes of the spectrum to be analysed at high resolution, turning what were once narrow single-channel searches into multi-channel, multi-target campaigns. Concepts of technosignatures also broaden. A technosignature is any observable sign of technology, whether it takes the form of a radio signal, a brief optical flash from a powerful laser, a characteristic pattern in the waste heat spectrum of a star system, or some other large-scale engineering footprint. Projects are proposed and sometimes carried out to look for bright short laser pulses from nearby stars which could be used as optical beacons. Ideas are developed for how an advanced civilization's energy use might alter the infrared output of its environment, perhaps by surrounding a star with structures that capture most of its light and re-radiate it at longer wavelengths. In principle, such changes could be noticed in all sky surveys that already map the heavens in infrared light. Through all of this, the practical limits of the search remain severe. The radio spectrum is wide, and there is no guarantee that alien transmitters, if they exist, would choose the same frequencies that early human theorists favour. The sky is vast, and only a tiny fraction of possible directions can be watched carefully at any given time. The time dimension adds another layer. A signal might be intermittent sweeping or short-lived, and many surveys only glance at each target for minutes or hours. Even within these constraints, the negative result stands out. No clear, repeatable, and independently confirmed signal has been found that resists all natural explanations and matches the profile expected from a deliberate artificial transmission. Candidate signals occasionally attract attention with bursts or patterns that look interesting on first inspection, but follow-up observations either fail to reproduce them or reveal mundane causes such as interference from human technology, satellite transmissions, or previously unknown natural phenomena. As the years pass, these null results accumulate. They do not prove that the galaxy is empty of other civilizations, but they do begin to chip away at some of the most optimistic scenarios, especially those in which many societies are broadcasting powerful, easily detectable beacons in all directions for long periods of time. If such a population of eager broadcasters filled the Milky Way, then some of their signals would likely have been noticed by now even with imperfect searches. The fact that none have been found suggests either that the number of such civilizations is small, that their transmissions are weaker, rarer or more narrowly directed than early models assumed, or that their preferred communication methods do not align with the channels human instruments are currently tuned to. At the same time, Earth itself has become a faint source of technosignatures. Since the advent of radio and television, the planet has leaked a sphere of radio noise into space expanding at the speed of light. Modern radar systems and high-power transmissions add to this fog. In principle, an advanced civilization with sensitive instruments could detect Earth as a noisy point against the background of the Milky Way. More recently directed signals, such as the famous message once beamed toward a star cluster from a large radio dish, have been sent as deliberate attempts to announce humanity's presence. These efforts are modest compared to the scale of the galaxy, and they highlight how thin the technosignature of a young civilization can be. For the Fermi Paradox, the current state of listening offers a mixed picture. On one hand, the systematic searches that have been conducted so far still cover only a tiny slice of the possible parameter space. Most stars in the Milky Way have never been observed in detail at all radio frequencies, and the total listening time toward any given target is often short. On the other hand, decades of increasingly sensitive observations have not produced the sort of unambiguous repeating signals that would instantly confirm the presence of another technological society. The sky, as far as current radio and optical technosignature searches can tell, remains quiet. This quiet does not yet have the weight of a final verdict. It may be that more comprehensive surveys with future instruments will uncover a network of faint narrow band transmissions or different forms of technosignatures that have so far been overlooked. But in the present, the absence of clear detections deepens the paradox. The Milky Way appears to contain vast numbers of planets, many in potentially habitable zones. Life on Earth arises quickly once conditions allow it. Evolution demonstrates that intelligence and technology are at least possible outcomes. A simple application of the Drake framework often suggests that multiple civilizations could exist. Yet when Earth listens for their voices, the instruments hear only natural sources and the noise of human technology. The galaxy looks from this vantage point like a theatre with seats for many actors, but no obvious sound from the stage. This widening gap between what seems plausible on theoretical grounds and what is actually observed prepares the way for Enrico Fermi's simple cutting question, which brings the paradox into sharp focus. Enrico Fermi's question enters the story at a point when the scientific and technological groundwork is already in place. By the middle of the 20th century, physicists and astronomers understand that the universe is large and old, that the Milky Way contains vast numbers of stars, and that nuclear energy can power both stars and advanced machines. Human rockets have only just begun to fly, but the basic physics of space travel is clear. In this setting, Fermi, an Italian-American physicist known for his clear practical thinking, raises the issue in an informal conversation with colleagues. The exact words and details of the exchange are less important than the simple, sharp idea behind it. Given a galaxy full of stars, planets, and long time scales, where are all the other civilizations that might have had a head start on Earth? The power of this question comes from the way it combines distance speed and time. The Milky Way is large, with a diameter of around 100,000 light-years, yet it is not infinitely large, and the speed of light, while high, is finite. If a technological civilization arises on one planet and decides to explore or settle the galaxy, it does not need to send ships that move anywhere near light speed. Even vessels that travel at a small fraction of that speed, perhaps using fusion reactions, solar sails or other plausible means, could in principle hop from star to star. If each voyage between neighbouring systems takes tens of thousands of years, and if new expeditions are launched in multiple directions from each new foothold, then over time a wave of exploration could move through the galaxy. When the numbers are sketched out, even with very conservative travel speeds and long pauses between journeys, the total time needed for such a wave to cross the Milky Way is surprisingly short compared to the age of the galaxy. Estimates vary, but many fall in the range of tens to hundreds of millions of years, a span that is tiny when set against the more than 10 billion year history of the galactic disk. In other words, if one civilization began to expand a few 100 million years ago, and if it persisted in that effort, there has been plenty of time for it to reach every part of the Milky Way many times over. The same logic applies to self-replicating probes, sometimes called von Neumann machines. If a society learns to build robotic craft that can harvest raw materials from asteroids or moons, make copies of themselves and continue onward, then an initial investment of a modest number of probes could seed an ever-growing network of explorers. Each probe might take a long time to travel between stars and to build its successors, but the number of active machines would grow over time, and the overall front of exploration could sweep through the galaxy on similar timescales to those of a slow but persistent colonization effort by living beings. For the Fermi Paradox, the details of motivational culture are not the first concern. The argument does not assume that every civilization must seek to conquer or permanently occupy every world it encounters. It simply notes that given enough time, even a small fraction of civilizations that choose to expand would be enough to fill the galaxy with signs of their presence. These signs might include settled planets, mining operations in asteroid belts, large engineering structures around stars, or dense networks of probes and beacons in interstellar space. Because many stars in the Milky Way are older than the Sun by billions of years, there has been ample opportunity for such expanding civilizations to arise, long before Earth's technological era. If any one of them began a program of large-scale exploration in the distant past and continued it for a significant period, the odds seem high that its traces would now be visible somewhere in the sky. Yet systematic astronomical surveys have not found clear evidence of such galaxy-spanning activity. Observations of the Milky Way structure do not reveal obvious artificial megastructures around large numbers of stars. Infrared surveys do not show a widespread population of systems whose radiation is dominated by the waste heat of hypothetical star-engulfing constructions. Planetary systems examined in detail mostly look natural, with distributions of planets' dust and gas that can be explained by standard astrophysical processes. This does not rule out the possibility of smaller-scale engineering or subtle interventions, but it does argue against a galaxy that has been thoroughly reshaped by many aggressive expansionist civilizations over hundreds of millions of years. Fermi's question also connects to time in another way. On Earth, technological civilization in the sense of a society capable of building radios, rockets, and computers occupies only a very brief interval compared to the age of the planet. If this pattern is typical, then many civilizations might rise and fall on different worlds without overlapping in time. In that case, the galaxy could host a long sequence of isolated technological eras, each separated by intervals of silence. However, the age structure of stars in the Milky Way again complicates this comforting picture. Some stars and their planets are billions of years older than the Sun. If civilizations arise on those worlds, their histories could unfold long before humans appear. Even if each one is short-lived, the large number of possible starting points and the long total history of the galaxy make it plausible that at least a few would last long enough to overlap or leave enduring artifacts. Self-replicating probes in particular could continue to function and spread long after their makers have vanished. The hard version of the Fermi Paradox emerges from the combination of these elements. The galaxy is old, many stars have planets, habitable conditions do not appear extremely rare. Life on Earth arises quickly once conditions permit, and evolution demonstrates that tool-using intelligence is at least possible. Simple models of expansion and exploration show that a single civilization with modest technology could, if it chose to spread detectable signs across much or all of the Milky Way in a fraction of the time available. Therefore, under a wide range of reasonable assumptions, one might expect a sky filled with evidence of past or present alien activity. Instead, the actual observations reveal a sky dominated by natural processes. Stars form, shine, and die according to well-understood physics. Galaxies interact and merge. Planets orbit in patterns consistent with gravity and initial conditions. No unambiguous large-scale structures or signals demand an explanation in terms of advanced civilizations. This mismatch between expectation and observation is what Fermi's question captures so well. Where are all the aliens that the simple argument suggests should exist? Are the initial assumptions wrong at a deep level? Is there a barrier that prevents civilizations from expanding? Do many societies choose isolation or subtlety over visibility? Or are human instruments and perspectives still too limited to see what is actually there? These possibilities point toward different families of solutions to the paradox. Before examining them, the narrative must consider one more ingredient: the idea that somewhere between the birth of stars and the rise of galaxy-spanning civilizations lies a sequence of difficult steps, one or more of which may be so unlikely that almost no worlds ever pass it. This concept takes shape as the Great Filter, a way of thinking about where in the long chain from matter to minds the main obstacles might lie. The idea of the Great Filter arises as a way to make sense of the long chain of events between the birth of a star and the appearance of a galaxy-spanning civilization. The Fermi Paradox highlights a simple tension. On the one hand, the Milky Way appears to offer many chances for life and intelligence to arise. On the other hand, there is no clear evidence that any civilization has gone on to fill the galaxy with obvious signs of its presence. The Great Filter frames this gap by suggesting that somewhere along the path from lifeless matter to advanced technological societies, there are one or more steps that are extremely unlikely. Almost all worlds, no matter how promising they seem, at first fail at one of these steps and never progress further. In this view, the silence of the galaxy is not an accident but a consequence of deep improbabilities hidden in the history of life and civilization. To make this more concrete, some thinkers list the key transitions that would have to occur for a planet to progress from basic chemistry to interstellar expansion. One such list, proposed by economist Robin Hanson, outlines a sequence that begins with the right kind of star system and moves through stages such as the origin of self-replicating molecules, the emergence of simple single-celled life, the appearance of complex single cells with internal structures, the development of sexual reproduction, the rise of multicellular organisms, the evolution of tool using animals with intelligence, the formation of an advanced technological society, and finally a period of sustained expansion or colonization. Each of these transitions can be thought of as a potential filter. If any one step is extremely hard to achieve, then only a tiny fraction of planets will ever pass it. The Great Filter hypothesis suggests that at least one of these steps is indeed that difficult. The crucial question from the point of view of the Fermi Paradox and for humanity's place in the story is whether the hardest filters lie mostly behind us or mostly ahead. If the most improbable transitions occur early in the sequence, then Earth might already have passed through them. For example, it might be that the origin of life itself, the transition from non-living chemistry to self-replicating molecules and cells, is extraordinarily rare. Perhaps the formation of complex cells with internal compartments like those found in plants and animals is a freak event that almost never happens. Or the jump from simple multicellular forms to complex organisms with nervous systems might require an unlikely combination of environmental and genetic changes that only a few planets ever experience. In this early filter scenario, the fact that Earth has life-complex cells, multicellular organisms and a technological civilization would mark it as a member of a very small and unusual group. The galaxy would then be filled with planets that stall at earlier stages. Many might never develop life at all, some might host only microbes, and very few would go beyond that. Under such conditions, the silence observed by radio telescopes and the absence of large-scale engineering in the sky would not be surprising. There would simply not be many advanced civilizations present at any one time, perhaps only one, and that one would be here. In a sense, this would make Earth an astonishingly lucky world, the beneficiary of a chain of rare successes that almost never occurs elsewhere. The Great Filter in this interpretation is mostly in the past. The alternative is that many of the early steps are not especially rare. If life tends to arise quickly once conditions allow, if complex cells and multicellular organisms are natural outcomes of evolutionary processes on many planets, and if tool using intelligence can appear in various forms, then the main bottlenecks may lie later in the sequence. The difficult steps might be those that involve long-term stability and restraint in the face of growing technological power. In this late filter scenario, many planets could host civilizations that reach a level similar to or beyond current human technology, but almost all of them fail to maintain that state for very long. They might destroy themselves through wars, environmental collapse, uncontrolled technologies, or accidents. They might fall victim to natural catastrophes that their science cannot yet prevent. They might choose paths that lead them inward rather than outward, abandoning large-scale physical expansion in favor of virtual or minimal physical footprints that leave few detectable traces. The net result would still be a quiet galaxy, not because advanced civilizations never arise, but because they do not persist in forms that are easy to see. From the standpoint of the Fermi Paradox, both versions of the Great Filter can explain the lack of evidence for other societies. In the early filter picture, almost no one ever reaches the stage where expansion is possible. In the late filter picture, many reach that stage but do not stay there long enough or in the right mode to reshape the galaxy in a way that current instruments could detect. The difference between these possibilities has deep implications. If the Great Filter lies mostly behind Earth, then the existence of a technological civilization here is a sign that an extraordinary sequence of unlikely events has already occurred. Humanity would be rare in the galaxy, perhaps unique in the observable universe, not because of any special destiny, but because almost no other worlds managed to pass the hidden test required to reach this point. The future in that case might be relatively open. The main dangers would be contingent, not forced by universal patterns. If the great filter lies mostly ahead, the situation looks more troubling. In that picture, the same processes that have brought human society to its current level might routinely lead to self-destruction or permanent stagnation on other worlds. The silence in the sky would then be a warning, a sign that civilizations which gain the power to reshape their environments and explore the stars rarely manage to do so in a stable, long-lasting way. In such a universe, humanity would be typical rather than exceptional, standing at a stage where many others have already stood, with most of them having failed to continue. It is also possible that the Great Filter is not a single dominant step, but a combination of several moderately difficult ones. In this blended view, many worlds fail at different points in the sequence, some never forming life, some never progressing beyond simple cells, others never developing intelligence, and others again breaking down under the pressures of technological growth. The overall effect can still be a galaxy that has room for almost no long-lived expansionist civilizations, even if no individual step is impossibly rare on its own. The Great Filter concept does not specify exactly where the main obstacles lie. Instead, it offers a way to organize thinking about the long chain of conditions that must be satisfied to turn a star system into a base for large-scale cosmic activity. It also connects back to the Drake equation, since the filters correspond to the low probabilities assigned to certain terms. A very small fraction at any stage can drastically reduce the final number of civilizations. For now, observational data provide only faint guidance. The early appearance of life on Earth might argue against a very strong filter at the abiogenesis stage, although the sample size of one limits firm conclusions. The complexity of eukaryotic cells and the rarity of technological intelligence in the fossil record hint that some transitions are hard, but they do not reveal how often similar transitions could occur elsewhere. The current absence of clear technosignatures in the Milky Way suggests that either expansionist civilizations are extremely rare, or they do not leave the kinds of marks that have been sought so far. As long as these uncertainties remain, the Great Filter remains more a framework than a resolved answer. It deepens the Fermi Paradox by pressing the question of where in the long history from atoms to minds and beyond the main barriers lie. It also sets the stage for different families of explanations for the apparent cosmic silence, ranging from comforting scenarios in which Earth has already passed the hardest tests, to sobering ones in which the most difficult challenges still await. When the Great Filter is viewed as something that mostly lies in the past, the story of Earth becomes a sequence of narrow escapes. In this picture, the quiet of the galaxy is not surprising, because almost no worlds manage to pass the same series of difficult transitions that Earth has already crossed. The Fermi Paradox then turns from a question about missing neighbours into a question about how many unlikely steps hide behind the familiar facts of Earth's history. The first candidate for a past filter is the origin of life itself. On Earth, life appears early once the surface cools enough for liquid water to persist, but the exact path from non-living chemistry to self-replicating molecules is still unknown. Laboratory experiments show that many building blocks of life, such as amino acids and simple organic chains, can form under a variety of conditions. However, the transition from a rich chemical soup to a system that can copy itself, store information and evolve remains unclear. It may be that this transition is extremely difficult, and that Earth's early success hides a series of rare coincidences, such as particular mineral surfaces cycles of wetting and drying, or unusual energy gradients that are seldom reproduced elsewhere. In that case, most planets with suitable conditions might host complex chemistry for billions of years without ever crossing the threshold into biology. A second candidate lies in the structure of cells. All complex plants and animals on Earth are built from eukaryotic cells, which contain internal compartments and a central nucleus. One leading hypothesis suggests that these cells arise from a rare event in which one simple cell engulfs another, and instead of digesting it, forms a stable partnership. The internal partner becomes a mitochondrion, providing efficient energy for the host. Such an event may require a precise balance of compatibility and timing, and there is little direct evidence that it has happened many times. If the emergence of complex cells is indeed a unique or nearly unique event in Earth's history, then many planets might host only simpler cells that never gain the energy budget needed to support large multicellular bodies and highly active brains. Later steps could also function as filters: the rise of multicellular life, the development of complex body plans, the invention of nervous systems, and the emergence of language capable of transmitting detailed knowledge across generations might all depend on particular chains of mutations and environmental pressures. On Earth, these chains include long periods of relative stability, interrupted by mass extinctions, climate swings, and shifting continents. Some of these disturbances open ecological space for new forms to flourish, while others nearly eliminate entire branches of the tree of life. The exact sequence of events that leads to a lineage of primates and eventually to humans is tangled and contingent. In a pass filter scenario, this tangle is not just one of many equivalent histories, it is one of very few paths that ever reach technological intelligence. Beyond biology, planetary and astronomical conditions might themselves act as filters. Earth orbits a stable, long-lived star and rotates at a comfortable distance where liquid water can exist on its surface. It has a large moon that helps stabilize its axial tilt, reducing extreme swings in climate. It possesses a magnetic field generated by a convecting core, which deflects stellar wind and protects the atmosphere from rapid loss. It also has plate tectonics, a global process in which the crust is recycled and nutrients are cycled between the surface and the interior. Each of these features may play a role in long-term habitability and in maintaining environments where complex life can thrive. If only a small fraction of rocky planets share this combination of properties, then the number of worlds that can support advanced ecosystems over billions of years may be much smaller than the number of planets in habitable zones. In this context, the early appearance of life on Earth does not mean that life is easy everywhere. It may instead reflect a rare alignment of planetary characteristics that make the transition from chemistry to biology almost inevitable once the right conditions exist, while most other planets never achieve those conditions in the first place. Taken together, these possibilities support a view in which Earth has already passed several of the hardest filters. The origin of life, the formation of complex cells, the rise of multicellular organisms with nervous systems, and the specific path to technological intelligence might each be much less likely than simple reasoning based on star and planet counts would suggest. If each step reduces the number of surviving worlds by many orders of magnitude, then it is no longer surprising that in a galaxy of hundreds of billions of stars, only one planet is currently known to host a civilization capable of building radio telescopes. From the standpoint of the Fermi Paradox, a strong past filter resolves much of the tension between expectation and observation. The galaxy can be full of planets and rich in opportunities, but the chain of events needed to produce a technological society is so restrictive that almost none of those opportunities are realized. The silence of the sky then follows naturally. There are no distant empires, no vast networks of probes, and no bright techno-signatures to detect because almost no other worlds ever reach the point where such things can be built. This explanation carries a double edge. On one side, it offers a kind of comfort. If the major barriers lie in the distant past, then humanity has already passed them, and the future is not constrained by the same hidden probabilities. Civilization might still face many challenges, but those challenges would not be part of a universal filter that almost all worlds fail. On the other side, it implies an extreme form of cosmic loneliness. Earth would not just be one interesting planet among many, but a rare exception in a galaxy of mostly simple or sterile worlds. The night sky filled with stars would hide almost no other minds, not because they choose silence, but because they never had the chance to develop. This scenario also faces its own uncertainties. It relies on the assumption that certain steps in Earth's history are genuinely improbable, in a cosmic sense rather than merely poorly understood. With only one known example of a life-bearing planet, it is difficult to distinguish between events that are intrinsically rare and events that simply occurred once in a process that might replay elsewhere in different forms. The early appearance of life and the long delay before complex animals both admit multiple interpretations. A past filter does not remove the paradox entirely. It shifts the emphasis. Instead of asking why existing civilizations do not fill the galaxy, the question becomes why Earth has managed to pass filters that almost all other worlds have failed. The silence of the Milky Way remains a clue, but now it points toward deep improbabilities in the early steps, rather than toward widespread failure in later stages. As the narrative unfolds, attention must also turn to the other side of the Great Filter argument, in which many of the early steps are common, and the main obstacles lie ahead of any young civilization that begins to wield technology on a planetary scale. In that view, the quiet galaxy may not be a sign that the hardest parts are safely behind, but a warning that the most dangerous filters attend the transition from local industry to long-term stable cosmic activity. When the Great Filter is viewed as something that lies mostly ahead, the quiet of the galaxy takes on a different meaning. Instead of implying that very few worlds ever reach the stage of technological civilization, it suggests that many may arrive there, but almost none manage to continue for long in a form that is visible on cosmic scales. In this picture, the early steps from chemistry to biology, and from simple cells to complex organisms, are not exceptionally rare. Life may arise on many planets, and intelligence capable of building tools may appear in multiple lineages across the Milky Way. The main difficulty, the place where most civilizations fail, comes later when those societies begin to wield powers that can transform their worlds and potentially extend far beyond them. From the standpoint of the Fermi Paradox, this late filter scenario is sobering. If the galaxy is filled with planets where life emerges readily and evolves toward intelligence, then there should be many technological civilizations scattered in space and time. Yet the absence of clear techno-signatures suggests that such civilizations are either very short-lived, or they adopt behaviors that keep them effectively invisible. One obvious family of late filters involves self-inflicted catastrophe. As a civilization develops advanced technology, it gains the ability to manipulate energy on large scales, store and transmit vast amounts of information, and alter its environment in ways that no previous species on its planet could manage. These capabilities bring benefits such as improved control over disease, access to new resources, and the ability to explore space. They also introduce risks that did not exist before. Weapons based on nuclear reactions, engineered pathogens, uncontrolled artificial systems, and large-scale environmental changes are examples of tools that can, in principle, destabilize or destroy the very infrastructure that supports the civilization that created them. On Earth, the emergence of nuclear weapons in the 20th century marks a clear moment when human society acquires the power to cause global damage in a short time. Later concerns about climate change, biodiversity loss, and emerging technologies add layers to this picture. None of these developments guarantee collapse, but they illustrate a general pattern. the same abilities that allow a civilization to shape its future also open paths to rapid failure. If similar patterns hold on other worlds, then many technological societies may face a period in which their continued existence depends on successfully managing complex global risks. A second family of late filters involves external catastrophes. Planetary systems are not perfectly stable. Large asteroid impacts, nearby supernova explosions, gamma-ray bursts, or abrupt changes in stellar activity can all threaten life on a planet. Over long enough timescales, some of these events are almost inevitable. A civilization may be unlucky and encounter a natural disaster before it has the capability to mitigate or avoid it. However, in many scenarios, the risks posed by self-created technologies may overshadow those from external sources, especially as a society becomes more interconnected and reliant on vulnerable infrastructures. Another possibility is that civilizations do not destroy themselves outright, but instead fall into long periods of stagnation or decline. They may exhaust easily accessible resources, lose social cohesion, or decide that further expansion is not desirable. In such cases, a technologically capable society might retreat into a lower energy, lower visibility mode. It could focus on maintaining a stable population and a modest level of comfort without building large structures or sending frequent signals into space. Over time, outside observers would see little evidence of its existence, especially if its activities are confined to the surface of a single planet or to small, well-shielded habitats. A more speculative class of late filters concerns changes in the way advanced societies use information and energy. As technology progresses, a civilization might shift much of its activity into virtual environments, distributed computing networks, or compact, efficient systems that radiate very little waste energy. If most of its experiences and interactions take place inside dense, optimized infrastructure, the external signature could be faint. From a distance, the civilization would not look like a sprawling empire of physical colonies, but rather like a subtle modification of existing planetary or orbital environments. Current surveys focused on bright radio beacons or large-scale engineering around stars might not be tuned to detect such low-profile arrangements. In all of these cases, the common theme is that there is a narrow window during which a civilization is both active and easily detectable at interstellar distances. Before it develops powerful technology, its signals are weak or absent. After it passes through a critical phase, it may either have destroyed itself, stabilized in a quiet mode, or transformed into a configuration that does not radiate prominent technosignatures. The result is a galaxy in which technological civilizations may be frequent in an absolute sense, but rare in the specific states that produce strong obvious signals. The Fermi Paradox becomes a statement about timing and vulnerability. If most technological societies do not survive for more than a small fraction of the time available in the galaxy, then the odds that two such civilizations will overlap and be visible to one another are reduced. Under this view, the silence in the sky is not necessarily due to a lack of other minds. It may reflect a pattern in which most of those minds do not remain in loud, expansive phases for long enough to be noticed. For humanity, this interpretation of the Great Filter frames the present era as a potentially critical stage. The same capacities that allow Earth civilization to send spacecraft to other planets, to broadcast signals into space, and to contemplate long-term futures, also bring it into contact with global risks that have no precedent in earlier history. The existence of a quiet galaxy with no sign of ancient long-lived empires could be read as a hint that most societies do not navigate this stage successfully. However, this conclusion is far from certain. The data are limited, and the sample of known civilizations consists of one. It is also possible that late filters are not universal, or that some civilizations do manage to reach stable, enduring forms that are simply hard to detect with present methods. In addition, the late filter scenario interacts with observational biases. Searches for technosignatures have so far focused mainly on radio, and to a lesser extent optical signals. If advanced societies prefer different channels, or if they deliberately avoid actions that would reveal their presence to unknown observers, then current surveys might miss them, even if they are common. In that sense, the apparent absence of long-lived visible civilizations could be as much a reflection of human assumptions as of cosmic reality. The late filter hypothesis deepens the Fermi Paradox by linking the silence of the Milky Way to the fate of technological societies. If many civilizations arise but very few endure in detectable forms, then the galaxy may be full of histories that end before they can reshape their surroundings on large scales. The question then becomes not only why the sky is quiet, but whether the quietness is a sign of a general tendency for civilizations to fail at the point where they gain the power to alter their destiny. Between the past filter and the future filter, Picture's the paradox stretches across the full arc from the origin of life to the long-term use of advanced technology. Neither resolution is fully supported or ruled out by current data, and both leave room for many variations. The next step in the narrative is to explore explanations that do not rely solely on extinction or improbability, but instead turn to the idea that advanced civilizations may exist and endure, yet choose or be forced to remain hidden, quiet or difficult to detect even in a galaxy that appears at first glance to be an inviting stage for contact. As thoughts about the Great Filter move from rare beginnings and dangerous futures to the behaviors of long-lived societies, another family of explanations for the Fermi Paradox takes shape. In these scenarios, advanced civilizations do exist in the Milky Way, and some of them endure for long periods, but they're difficult to notice because they are quiet, hidden, or deliberately restrained in their dealings with a wider galaxy. The silence of the sky is then not a sign of absence, but a consequence of choices, strategies, or constraints that keep most activity below the threshold of current detection methods. One simple possibility is that mature civilizations lose interest in broadcasting loud signals into space. Early in their technological development, they may experiment with powerful, inefficient transmitters that leak energy widely, much as human society once filled parts of the radio spectrum with strong analog television and radar signals. Over time, however, communication technologies can become more focused and efficient. Networks may shift toward fiber-tightly beamed links and low-power local signals that spill far less into interstellar space. In that case, the period during which a civilization radiates easily, detectable broadcasts into the galaxy may be brief. After that, its communication infrastructure becomes almost invisible at great distances, even though it might be dense and vibrant on local scales. Another possibility is deliberate radio silence. Civilizations that become aware of the risks associated with announcing their presence to the cosmos might decide to minimize their electromagnetic footprint. They may consider that the distribution of other societies is unknown, that some could be hostile or simply reckless, and that any loud beacon could reveal their location to entities with unknown intentions. In response, they could adopt policies that restrict high-power transmissions, mask their signals within natural backgrounds, or confine communication to cables and narrow beams that do not travel far beyond their systems. In this view, the absence of obvious beacons is a form of self-protection. Many societies might share an unspoken agreement arrived at independently that caution is wiser than open broadcast. Hidden civilizations need not rely only on quiet communication. They may also seek to reduce or disguise large-scale engineering signatures. An advanced society capable of harnessing vast energy resources could in principle build enormous structures around its star or rearrange its planetary system. However, such activities might not be energetically or ethically attractive. Civilizations that place a high value on environmental stability minimal interference or aesthetic considerations could favour compact, efficient designs that integrate with existing planetary and orbital structures rather than replacing them. They might embed their habitats in asteroids' icy moons or carefully manage planetary surfaces, keeping total waste heat emissions only slightly above natural levels. From a distance, their star system would appear ordinary, with no obvious signs of artificial reshaping. There is also the idea of a galactic version of a protected reserve. In this scenario, one or more early civilizations, or a loose community of them, reach a level of understanding and coordination that allows them to influence the development of younger societies. They might adopt a principle of non-interference, choosing to observe without direct contact until a civilization reaches certain thresholds. This concept mirrors some human ideas about preserving natural ecosystems or uncontacted cultures, but on a much larger scale. The practical implementation could involve careful monitoring, combined with subtle interventions to keep advanced infrastructure hidden from emerging observers. For a young society scanning the sky with primitive instruments, the galaxy would look natural and empty, even if it were quietly watched from afar. A related possibility is that of cosmic camouflaging. Civilizations may possess technologies that allow them to manipulate their detectable signatures, making them blend into the background of normal astrophysical processes. They could, for example, shape their waste heat output to mimic that of dust clouds, or modulate their emissions so that they appear as common variable stars or other known phenomena. In an extreme version of this idea, an advanced society could even modify the local distribution of matter and radiation to erase or mask any evidence of earlier large-scale engineering projects. While speculative, such scenarios illustrate how the absence of obvious techno-signatures does not necessarily imply an absence of activity. Under the theme of self-imposed limits, some explanations for the Fermi Paradox suggest that expansion itself may be culturally or philosophically out of favour. A civilization might decide that indefinite growth and colonization are undesirable goals. It may conclude that sustainable use of resources within a limited volume, combined with inward development of knowledge art or virtual experience, offers a more stable path. If many civilizations independently arrive at such conclusions, the Milky Way could be populated by societies that are advanced but spatially modest. They would leave few traces beyond their home systems or local clusters of habitats, especially if they take care to manage their outputs. Another factor that could contribute to the appearance of emptiness is the narrowness of human search strategies. Most organized hunts for technosignatures so far have looked for specific kinds of signals, narrow-band radio transmissions, bright optical pulses, or unusual excesses of infrared radiation. The assumption has often been that other civilizations, if they wish to be noticed, or if they use certain technologies, would generate patterns that stand out in these channels. However, if their preferred communication methods rely on particles fields or other carriers that current human instruments do not monitor, then even energetic and frequent exchanges among them would pass undetected. The same applies if their engineering focuses on computational efficiency quantum systems, or structures that operate close to physical limits with very little wasted energy. From that perspective, the search so far might be compared to listening for drum beats in a city where most traffic moves silently on fiber networks. For the Fermi Paradox, the notion of hidden or quiet civilizations shifts emphasis from absence to detectability. It allows for a galaxy that contains many advanced societies whose existence is compatible with current observations because their visible footprint is small by design or by technological evolution. The paradox becomes a question of whether the silence reflects a true lack of other minds or merely a mismatch between their behaviors and the expectations built into human surveys. This family of explanations does not remove the need for filters or risks, but it softens one specific prediction of the simple expansion argument. Even if some civilizations can spread among the stars, they may do so in ways that leave few obvious scars. They might travel in small numbers, create lightly inhabited outposts, or prefer exploration and remote sensing over heavy colonization. Such patterns would not produce the bright galaxy-wide engineering signatures once imagined in early discussions of supercivilizations. Instead, the Milky Way would remain visually dominated by natural processes with advanced activity, tucked quietly into its existing structures. In that scenario, Earth's current impression of isolation becomes a local truth rather than a cosmic absolute. From one young planet's point of view, the galaxy can appear empty, even if on other worlds or in distant shielded habitats, other observers are also looking out guided by their own rules of caution, restraint or indifference. As the Fermi Paradox unfolds through ideas about fertile galaxies' possible filters and hidden civilizations, another thread runs quietly alongside all of these discussions, the limits of what can currently be seen and measured. Every statement about a silent Milky Way rests on data gathered by instruments with finite range, finite sensitivity and finite time. The absence of clear technosignatures so far is a real result, but it is also shaped by selection effects, by the small slice of the possible cosmic landscape that present methods have examined. To understand how strongly the paradox presses, it is necessary to look closely at how narrow that slice still is. Radio searches, which form the backbone of many techno-signature efforts, illustrate this point clearly. The radio spectrum extends across a wide range of frequencies, yet any individual survey can only monitor a limited band at once. Over the decades, different projects have scanned different segments of this spectrum, but the total coverage in both frequency and time is still a tiny fraction of what is theoretically possible. Many stars have been observed only briefly, sometimes for minutes or hours at selected frequencies. If a distant civilization were to send out a narrow band transmission that swept across the sky on a schedule of days, months, or longer, there is no guarantee that a telescope on Earth would happen to be listening in the right direction, at the right frequency, and at the right moment. A signal that is intermittent, highly directional, or short-lived could easily go unnoticed. The same is true for surveys looking for optical technosignatures such as intense rapid laser pulses. Telescopes can watch only certain regions of the sky at any given time, and their fields of view are limited. A civilization might use optical beams for communication in ways that rarely intersect Earth's line of sight. Even if a beam did pass across Earth's position, the chance that a suitable detector would be pointed at the correct part of the sky during the brief interval of the pulse is small. In practice, the observational window is narrow compared to the volume of space-time in which such signals might occur. Infrared searches for large-scale engineering, such as structures that alter a star's output, face different challenges. All sky surveys in infrared light have been performed, and catalogues of sources have been built, but interpreting those catalogues is complex. Many natural processes can produce excess infrared emission, including dust star formation regions and the outer parts of galaxies. Distinguishing a subtle artificial signature from these natural backgrounds is difficult, especially if advanced civilizations are disciplined in managing their waste heat, or if their constructions are small compared to the total luminosity of their host stars. Searches for unusual infrared sources may therefore miss systems where technology is present, but modest or well integrated into the existing astrophysical environment. Beyond these technical considerations, there is also the question of distance. Most detailed technosignature searches concentrate on stars within a relatively small part of the Milky Way, often within a few thousand light-years. This is a tiny subset of the full galactic disk which stretches much further in all directions. Radio and optical signals weaken with distance, and interstellar scattering can blur or distort them, Even if many civilizations exist in the outer regions of the galaxy, or on the opposite side of the disk, their signals might be too faint, too smeared, or too far outside the frequencies currently monitored to be detected with present instruments. Time adds another layer. The duration of human listening and looking efforts is minuscule compared to astronomical timescales. Systematic searches for technosignatures have been conducted for only a few decades. By contrast, stars live for billions of years, and even short-lived civilizations might endure for hundreds of thousands of years. The overlap between the brief window in which Earth has been listening and the potentially long but still finite lifetimes of other societies may be small. It is possible that many civilizations existed in the past and have already vanished, leaving behind artifacts that are too subtle to see from afar. It is also possible that others will arise in the future after current surveys have ended or changed form. The present moment provides only a single temporal cross-section through a much longer history. There is also a bias in the kinds of signatures that have been sought. Many early and current searches focus on technosignatures that resemble human technologies scaled up or adjusted for interstellar use. Narrow-band radio beacons, bright optical flashes, and large waste heat sources are examples. This emphasis is natural because it is easier to look for phenomena that fit known patterns. However, if advanced civilizations rely on communication methods and energy systems that differ significantly from those currently imagined, their presence might not register in existing surveys. Subtle modulations of existing astrophysical sources, low-power networks embedded in interplanetary space, or communication channels based on particles that are not routinely observed, could all fall outside the reach of standard instruments. From this perspective, the apparent silence of the Milky Way is partly a reflection of human assumptions about what alien activity should look like. A further consideration is the difficulty of distinguishing unusual natural phenomena from artificial ones. The universe produces many signals that at first glance might resemble technosignatures. Pulsars, for example, were initially surprising because of their regular radio pulses. Fast radio bursts present another class of brief, intense radio events, whose origins are still under study. Each time a new type of source is discovered, there is a period during which artificial explanations are considered and then set aside as natural mechanisms are understood. This pattern means that any weak or ambiguous signs of technology could be concealed within a larger population of poorly understood natural phenomena. Without definitive markers, the cautious interpretation is to attribute new signals to nature until strong evidence to the contrary appears. All of these limits do not remove the Fermi Paradox, but they do soften its edges. The lack of detected technosignatures so far is compatible with several possibilities. There may truly be very few advanced civilizations, in which case the chances of detecting them with limited early-stage surveys are low. There may be many civilizations, but most may be distant, quiet, short-lived, or operating in modes that do not produce the signatures being sought. There may be hidden societies that deliberately manage their visibility. Or, as some argue, the current scale of observation may simply be too small to draw strong conclusions either way. At the same time, the growing knowledge of exoplanets, the early appearance of life on Earth, and the basic expansion arguments keep the paradox from dissolving completely. The galaxy still looks in broad terms like a place where life and intelligence could arise in many locations. The fact that current instruments have not yet found clear evidence of other civilizations remains a notable fact, even if it is not final. The tension then moves into a more balanced form. On one side stand the reasons to expect other technological societies somewhere in the Milky Way. On the other side stand the real but limited search efforts and the many ways in which civilizations might be difficult to detect. The silence heard so far is no longer taken as a definitive answer, but as one more piece of incomplete information in a story that is still unfolding. This recognition prepares the ground for a final narrowing of focus, in which Earth is seen not only as a planet that wonders about others, but as a young listening post in a galaxy whose full population of minds, if they exist, has yet to be mapped. On a small world in one spiral arm of the Milky Way, the threads of the Fermi Paradox come together in the present moment. Earth orbits an ordinary star that has shone steadily for billions of years, and on its surface a technological civilization has arisen that is able to build instruments, record data, and ask systematic questions about the universe. From this planet, the sky is no longer just a backdrop for myths or navigation. It is a field of measurement in which every point of light can in principle be studied for clues about its nature. In this sense, Earth has become a listening post, a place where matter that once drifted in interstellar clouds now sits inside radio dishes, optical telescopes and digital detectors all aligned to gather signals from the wider galaxy. The people who build and operate these instruments do so with many goals. They measure the expansion of the universe, study the life cycles of stars, and trace the distribution of dark matter. They also quietly but persistently listen for indications that other minds are at work beyond the solar system. Arrays of radio antennas scan wide swathes of the sky, searching for narrow band signals that do not resemble natural sources. Sensitive optical instruments test whether brief flashes of laser light arrive from nearby stars. Space telescopes examine exoplanets in reflected and transmitted light, looking for atmospheric signatures that might hint at the presence of biology. Catalogues of stars, planets, and galaxies grow year by year, each entry a potential context in which the question of other civilizations might eventually be framed. At the same time, Earth itself continues to send out weak techno-signatures. Radio, television, and radar emissions leak into space, forming an expanding shell of noise that now extends for more than a human lifetime of light years around the planet. Deep space probes move outward, carrying small plaques and recordings that encode basic information about their makers. Powerful transmissions, though rare, have been aimed at selected targets in symbolic gestures of contact. In practical terms, these efforts are modest, and the total volume of space reached by strong, clearly artificial signals from Earth remains tiny compared to the size of the Milky Way. Still, they mark the beginning of a new phase in the planet's history in which its presence can in principle be inferred from afar by watchers with suitable instruments. From this vantage point, several broad possibilities remain open. One is that Earth is early. In this scenario, the processes that produce life and intelligence are not rare, but the time needed for many civilizations to emerge has not yet passed. The galaxy may be in a phase where the first wave of technological societies is only beginning to appear. In such a universe, the current silence would not be permanent. Over future millions of years, more and more worlds might light up with signs of technology, and the Milky Way could gradually shift from a quiet to a busy state. Another possibility is that Earth is rare. The early appearance of life, the specific cellular innovations that underpin complex organisms, and the long chain of contingent events that lead to a technological society may indeed be highly improbable, even if they are not strictly impossible. In that case, the galaxy could contain countless planets where life never starts, or where it remains microbial or simple for all time. A small number of worlds might host complex ecosystems, but never produce species that build machines and study the sky. If this picture is correct, then Earth may be one of very few, or even the only planets in the Milky Way, where a civilization has reached the stage of sending radio signals and launching spacecraft. The quiet sky would then be an honest reflection of a sparse population of minds. A third family of possibilities is that Earth is neither very early nor uniquely rare, but simply not yet tuned to the right channels or scales at which other civilizations make themselves known. Advanced societies, if they exist, might communicate using methods that current instruments do not monitor, or they may prefer modes of activity that blend into natural backgrounds. They may be present at distances or locations that have not yet been surveyed in detail. The absence of clear detections so far would then be a function of incomplete searching and incomplete understanding rather than a final verdict. The future development of astronomy, including more sensitive radio arrays, larger optical and infrared telescopes and new kinds of detectors, would gradually test this idea by widening the range of technosignatures that can be sought. In all of these scenarios, Earth's role as a listening post remains significant. The planet carries a unique combination of circumstances. It hosts a biosphere that has persisted for billions of years, a technological society that can ask precise questions about its situation, and a suite of instruments that can reach far beyond the solar system in both observation and exploration. Although these capabilities are young on cosmic timescales, they are already enough to place constraints on some of the most optimistic visions of a galaxy filled with loud, easily detectable civilizations. The lack of obvious signals, megastructures, or unambiguous engineering signatures does not prove that the Milky Way is empty of advanced life, but it does shape the range of stories that can reasonably be told about that life. It narrows some paths and leaves others open. As each new survey is completed and each new catalogue compiled, the map of what is known grows denser and the space of unknowns shifts. The Fermi Paradox in this light is not a static puzzle with a single missing piece. It is a moving boundary between what has been observed and what remains untested. Every improvement in instruments, every extended search, and every new discovery of a planet, a biosignature candidate, or an unusual astrophysical phenomenon changes the balance between expectation and evidence. The paradox persists because both sides of that balance evolve. Knowledge of habitable worlds and life's resilience tends to increase the expected number of civilizations. Limits from technosignature searches tend to reinforce the impression of silence. Earth civilization stands at the point where these trends meet. It occupies a brief interval between a long past in which it did not exist and a long future whose shape is unknown. During this interval, it has the ability to look outward to test hypotheses about the galaxy and to reflect on what the absence of clear signs of others might mean. Whether the main filters lie behind or ahead, whether advanced societies are rare, short-lived, hidden, or yet to form remains unsettled. For now, the only confirmed case of a planet that wonders about the Fermi Paradox is Earth itself. The Milky Way stretches around it full of stars, planets, and possibilities, but silent enough at the present limits of observation that the central question stays open. Where are all the aliens that simple reasoning seems to allow? Are their worlds dark, their signals brief, their technologies quiet, or their histories already over? Or is the current silence just a temporary feature of a young search? The answers, if they exist, lie somewhere beyond the reach of present evidence, waiting in futures where new instruments, new discoveries, or new perspectives may shift the balance between expectation and observation once again.